Hey folks, in this tutorial we're going to be going through the 2019 WACE physics exam. Enjoy. Okay, so question one's a pretty straightforward one, and it's one of the easiest in the exam. So the first part is drawing an arrow to show the direction of the flow of conventional current. So your current's going to be flowing from positive to negative, so you could either draw an arrow that's going away from the positive, or you can also draw it that goes towards the negative over here. The second part is to draw an arrow showing the direction of the force on this particular rod. So if you have your current, it's going to be going sort of into the page, that's your thumb, and then you get your fingers and they point upwards, then your palm should face towards the right, and there is your second mark. So then to calculate the magnitude of the force, what you want to use is F equals ILB. Your current is going to be 1.5 amps. Your length is 30 centimeters, so 0.3 meters. And your magnetic field is 0.4 Tesla. So for that point there, you get yourself a mark. And then if you put that in your calculator, you should end up with 0.180 to 3 significant figures, newtons. Cool. Okay, so for question 2, what you're looking at is the apparatus demonstrating the photoelectric effect. There's 2 changes that you need to look at. The first of these changes is that you increase the wavelength from 450 to 490. So by increasing the wavelength, what you're doing is you're decreasing the amount of energy of those photons, which means that you're decreasing the amount of energy that those electrons will have when they're ejected. An important assumption here is that the frequency of the light remains above the threshold frequency. So the same number of, every time a photon hits the target metal, then it will eject a photoelectron. So for the initial current, you'd expect it to be unchanged, and that's because what you've been told in the question is that the photons per second remains unchanged. So if each of those photons is still going to be releasing an electron, then the current going through this ammeter will remain unchanged. However, because you have less energy being given to these electrons, they're going to have less kinetic energy as they leave the target, which means that the potential required to stop them from reaching the other side of the apparatus is going to be less. So we can say that the final voltage is going to be decreased. And so for change 2, we've got the wavelength being decreased, but the photons per second is now increased. So by decreasing the wavelength, you're going to be increasing the energy, but first of all, we want to see, we notice straight away that the photons per second is going to be increased. So if you're increasing the number of photons per second, that means you're going to be releasing more electrons, and by releasing more electrons, you're going to have an increase in the current that you'll observe. And because you're also increasing the energy, because you're decreasing the wavelength, you can expect that the potential required to stop those electrons from reaching the other side will also increase. So for question 3, you've got a magnet which is going to be moving towards this coil over here. And so the magnet, a permanent magnet, has a magnetic field. So this one will sort of look like this, and so on, and coming around. And as this magnet moves towards the coil is going to be experiencing a change in magnetic field going through it. So that'll induce an EMF across the two sides of that coil. So the question's asking, to using an appropriate equation from the formula and data booklet, explain why you have a larger EMF if the magnet was being moved at a greater velocity. So the first thing, the equation that I would use would be that the EMF is equal to, so this is from the data booklet, the change in flux over time. So that's the equation that I would use. And I would also go as far as to say that therefore the EMF that's induced, we can say, is inversely proportional to the time. So we want to sort of mention that since the number of turns in the coil is the same, and the change in flux is also the same, because we're not going to increase or decrease the amount of flux lines that that magnet is dishing out. But we're increasing velocity, right? So if we're increasing the velocity, that'll result in a decrease the time for that flux to occur. Change in flux to occur. So then I can say, therefore, increasing velocity would result in an increased EMF. Okay, so the way we would award the marks for this one might be that you would get probably 1 for here, and looking at their marking key, I think you're also going to receive a mark for pointing out that the number of turns and the flux also remains the same. The relationship between velocity and time would also be given 1, and I'd expect that referring back to the question to sum up your results, or to sum up your explanation, would also earn you a mark. And there we go. Okay, question 4 is a pretty straightforward one. What you've got is a moon orbiting Saturn, and it's giving you some data, and you need to figure out the gravitational field where Titan is currently orbiting. So you're going to use this formula, G equals big G, big M on R squared. So your big G is 6.67 times 10 to the negative 11. And the mass that you've been given for Saturn is 95 times the mass of the Earth. So the mass of the Earth is 5.97 times 10 to the 24 kilograms. And then you're going to divide that by, now all of this needs to be squared, it's probably a common mistake. So the radius is going to be 1.22 times 10 to the 6. Now it's in kilometers, so you need to make sure that you then go 10 to the 3. And you square that. Now if you put that in your calculator, what you should get is 2.54 times 10 to the negative 2, or 0.0254. And then at the bottom here, it's interesting, it's asking you for newtons per kilogram and meters per second squared. They are the equivalent of each other, so you should have 2.54 times 10 to the negative 2 there, and 2.54 times 10 to the negative 2 there. Now the mark allocation was 1 here and 1 there, and I think you got a mark for the for picking out the radius as being multiplied by 1,000, so you get a mark for that one, and a mark for the overall formula, or maybe 2 marks I think you would get, yeah. So 2 marks for how you applied that, so yeah, it's out of 5 marks. And that's it. Okay, so question 5 is also one of the easy ones in the exam. It's just giving you an energy value and it's asking you to convert that to mass. So you're going to start with the mass energy equivalent formula and rearrange the equation. So your energy value is given to you in 126 giga electron volts. So that's 126 times 10 to the 9 electron volts over c squared. So now we need to do a conversion. So we need to get that 126 times 10 to the 9 and convert that to joules. So we're going to multiply that by 1.6 times 10 to the negative 19. And we're going to divide that by 3 times 10 to the 8 squared. And if you put that in your calculator, you should get 2.24 times 10 to the negative 25 kilograms. So the mark allocation would be, you'd probably get 1 for that rearranging. You'd probably get 1 for this conversion here, and then the rest of it will be down here at how you obtain your answer. There we go. Okay, so question 6 shows a system that's in equilibrium. You've got a rigid strut here that has a load acting on it from the top, and then you've got a cable that's sort of pulling back on it. And then you've got the hinge where you're going to have the reaction force occurring. So the first part of the question is saying that a student draws this diagram of all the forces acting on it, like a free body diagram, and they're saying that it's wrong, and they're asking why is it wrong. So it's saying here with specific reference to the conditions required for equilibrium. So immediately, since it's a force diagram, I can see a problem here. So I'm going to say that, well, for equilibrium to actually occur, we need to have the sum of all the forces equal to be 0, but they're not. So I'll say which is not the case. Now, how do I know this? Well, if I just take a look at this strut here, or the tension along this line is acting to the left, which means I need to have another force that's acting at some point to the right. And you can see there is no arrows there that are acting to the right, which means that it's not in equilibrium. So I would say, so no rightward force to counteract the horizontal component of the tension. Therefore, net unbalanced force exists. Right, so looking at their answer key, they're also sort of saying you get a mark for this one and some sort of explanation as to what that means would be your next mark. So for part B, it's saying use the diagram below, show what changes should be made to correct it. Calculations are not required. Okay, so I don't think this would have been necessary, but I would have drawn the downward force here because that has to act along that line. The tension force also has to act along this line, and we expect the center of mass to also have a downward force. So what's actually needs to be different would be the force coming from this hinge. So if we look at the one at the top, you can see that it's going to the left, and that's causing the problem. What our force needs to actually do is go to the right. So I would suggest a force that counteracts, in terms of the vertical component, it needs to counteract all the downward forces here, and it also needs to go a little bit to the right. So I would draw something like this. Now the marking key just means that you need to have it to the right, and then you get your mark, and it needs to show some sort of vertical component. It doesn't specify, but I assume it means up to get that extra mark. And there we go. Okay, so in question 7, what you've got is a situation where you have a lightweight ball which is being pulled to the right by the electric field. It's also being pulled downwards by gravity, and the tension in this sort of rope or string is holding it in place. So the first part of the question is to draw a vector diagram of the forces acting on the ball. I would actually prefer to first draw a free body diagram, so I'm going to do that on top of this diagram. You've got a force acting down, which is going to be your force due to gravity, and you're going to have a force acting this way, which is your electric field, and you've also got a force acting along the rope, which is going to be the tension, so I'll just call that T for tension. Although it's not asked for, that's going to help me when I come up to part A. So to draw the vector diagram, what I would say is I would draw the tension force first, because I know that then I have the gravitational force acting downwards directly like so, and this angle here corresponds to the angle in this diagram. And then I have another force acting to the right, and that is your force due to the electric field. And it is in equilibrium. The pith ball is just being suspended there. So for part B, it's asking to calculate the angle between the string and the charged plate. So to find theta, I basically just need to find the magnitudes of two of these sides. Now, the tensional force isn't given to you in the question, so from this point I know that I need to work out the force due to gravity and the force due to the electric field. So let's start with the electric field. So from your formula sheet, you've got this equation here, and rearrange that, and you can get the force due to the electric field is equal to the electric field itself multiplied by the charge. So the electric field is 95. And the charge is due to a large number of electrons, so 2 times 10 to the 12 times the charge of an electron, 1.6 times 10 to the negative 19. And what you should get is 3.04 times 10 to the negative 5. And that'll be in newtons. And then I can get my force due to gravity. I should put newtons there. The force due to gravity is probably the easier one, and that's just your mg. So that's going to be, it's given to you in the question, 75 times 10 to the negative 6 times 9.8, and you end up with 7.35 times 10 to the negative 4 newtons. Okay, so now that I've got the size of Fg and Fe, so these two at the top here, I can then work out the angle between them. So I know that the tan of theta is going to be equal to, so opposite over adjacent, so Fe divided by Fg. So I can put that in as, so I then know that theta is going to be equal to the inverse tan of 3.04 times 10 to the negative 5 newtons divided by 7.35 times 10 to the negative 4 newtons. And what I get is 2.369 degrees, or what I write down here is 2.37 degrees. Okay. Okay, so looking at the marking key, you would have got a mark for knowing the relationship between the angle and those forces. There were 2 marks allocated to the electrical field calculation. There was 1 mark allocated to the gravitational field calculation, and then getting your answer down here was that final mark. There we go. Alright, so in question 8, you've got a cyclist that's going over a hump. You've got a velocity there, and you've got a mass and the radius, so it looks like a pretty straightforward question. What it's asking for is the magnitude of the reaction force. So in this situation, you've got a number of forces acting on that cyclist. So the net force acting on that cyclist would be the centripetal force, right? And then that should be made up of 2 components. One would be the force of gravity, and then that will, on top of that would be the reaction force from the ground, which is why you have this resultant centripetal force there. So what you can do to solve this would just be starting with that assumption. So the centripetal force is going to be equal to the force due to gravity, add that reaction force. Or in this particular case, if I were to sum those up, if I were to say downwards is positive, I would say mv squared on r is equal to mg. And since the reaction force is acting upwards, then I would say subtract that reaction force, like so. So now that I've got the directionality sorted, I can say that the reaction force is therefore going to be equal to mg take mv squared on r, and subbing those values in, 72 times 9.8 subtract times 6 squared over 4.8. Now at this point I immediately notice that the apparent weight will decrease. So you've got mg subtract a certain number, which means that you will feel lighter at the top of the hill, and that's consistent with what we expect. So I can continue on, and then what I get is 165.6 newtons, and down here I'll get that the 3 significant figures, so 166 newtons. And there we go. Okay, so in question 9, it's asking to use relevant formula to explain why the time dilation is negligible at a speed of 100 kilometers per hour. So the first thing you want to do to get that free mark is to sort of talk about time dilation with its formula. So it'll be 1 take v squared on c squared, and there's your first mark, essentially guaranteed for you there. Now a lot of students did substitution to answer the question, but I'm going to try and do it using the formula itself. So if I find the velocity first is 100 kilometers per hour, so if I convert that, that's going to be 27.8 meters per second. So I would say that since 27.8 meters per second is much, much smaller than 3 times 10 to the 8 meters per second, then this factor, the v squared on c squared, will come very close to 0. So if that goes very close to 0, the time will become very close, the measured time will be very close to the proper time. And something along those lines is how I'd explain it, but subbing in the values helps too. Okay, in question 10, you've got a graph of wavelength and momentum, and it's talking about the de Broglie wavelength. Part A says, give a possible relationship between the wavelength and momentum based on the shape of this graph. So I would be tempted to say it's an inverse relationship. And you can go even further and suggest that the wavelength is inversely proportional to the momentum. Now, something in the marking key that sort of struck me was the use of this proportionality instead of equals. If you used equals, then I don't think they would have given you the full mark for that. So just keep that in mind. For part B, describe how the data used to generate the graph could be reorganized to produce a straight line graph. So if I'm saying that the wavelength is inversely proportional to the momentum, then I can, if I plot that wavelength versus 1 on momentum, then I would expect to get a straight line graph. And that's all they're really asking for in that particular question. What would the gradient of the straight line from part B represent? So if I'm plotting the wavelength versus 1 on P, if I look at my formula sheet, I can see that there is this wonderful formula here. So if I'm plotting lambda on the y and 1 on P as the x, then what I'd expect to have is Planck's constant. Okay, and ignoring relativistic effects, calculate the momentum of a particle with a wavelength of 2.5 times 10 to the 2 nanometers. Okay, so this seems like a pretty straightforward calculation. You start with the formula that you've got in your formula sheet, and then you end up with the momentum's equal to Planck's constant over lambda. And I sub that in to get 6.63 times 10 to the negative 34 over 2.5 times 10 to the 2. Now it's in nanometers, so it's 10 to the negative 9. And I put that in my calculator and I get 2.652 times 10 to the negative 27. Now, three significant figures, it's 2.65, no worries. But the units here, just put the standard units in, since the numbers we've put in are all the SI, so we can come through and just that's kilograms, meters per second. Mark allocation would have been 1 for that, 1 for that, probably 1 for this, and you also got 1 mark just for the formula over here. And there we go. Okay, so in question 11, it's the last question of the short answer section. You've got Chloe, who's in a spaceship, and she's passing by a spaceport where you have Zhang. And Zhang is measuring the time taken for Zoe to get between 2 beacons, and he'll be working out the velocity from that. So part A is asking how long will it take, according to Zhang, for the spaceship traveling at 0.8 c to go between the 2 beacons. So that's a simple calculation of time is distance over velocity. The distance is 1,000 meters because that is the distance measured by Zhang, and the velocity is 0.8 times 3 times 10 to the 8. And what you should get is 4.17 times 10 to the negative 6 seconds. And that's only worth 1 mark, which is a bit harsh, but there you go. Part B is calculate the distance Chloe observes between the beacons before she passes the first beacon. So in other words, what is the distance between the 2 beacons according to her? So you would use your length contraction formula. And so 1,000 is what Zhang has measured, and that would be the proper length, 0.8 squared, and you should end up with 600 meters. Cool, and that one's worth 2 marks, so I think you get 1 mark for that bit and 1 mark for that bit. Okay, now part C is a little bit of an interesting one. You want to say something along the lines of, let's have a look. So the length contracts for both observers, I reckon, and if you wanted to get specific, you could say, so you can say Zhang observes the ship length contract while Chloe observes the distance between the beacons contract. So they're both correct in their own reference frames. Now you can probably get 1 to 2 marks from that bit there, but where the other 2 marks come from, your description of why length contracts differently for each observer. So in order to measure the length of something, what you need to do is figure out the locations of the endpoints of that object. So for the spaceship, it would be either side of the spaceship, and for the beacons, it'll be each of the beacons. And you need to know these positions at the same time or simultaneously. And this is where the idea of simultaneity being different for each observer comes into play. So what you would need to do for this question, for the second part of this question, is sort of explain essentially that. And it's not probably something that I would have gone to straight away, but for a 4-mark question asking about length contraction and why it happens, that's probably the level of detail that you should go into. And it probably does stretch deep into the syllabus there a little bit. Okay, so moving on to section 2 now, and we have question 12, which is about a ball that rolls down a ramp when it's on top of a table, and then it rolls off the table onto the floor. So part A is asking to use the conservation of energy to get the speed of the ball once it's finished rolling down the ramp. So you know that the potential energy at the top of the ramp is going to be equal to the kinetic energy at the bottom of the ramp. So you can say that mgh is going to be equal to 1/2 mv squared. Immediately you notice that the masses will cancel out, and you want to solve for the velocity. So you've got v is equal to square root of 2gh. If you sub those values in, you'll get the square root of 2 times 9.8 times 0.3, and you'll end up with 2.42 meters per second. The marks allocated for this bit would be 1 for the results, 1 for coming up with this equation, and there you go. So part B, you're looking at calculating the distance that it travels horizontally. So to know that, you know that the distance it travels will be equal to the horizontal velocity multiplied by the time that it's in the air for. So you need to solve for the time that it's in the air for. So to do that, what you want to do is, vertically speaking, you have S equals a half AT squared. So that means your T is going to be the square root of, what's that, 2 S on A. Or in this case, it's actually 2 times the height that it's falling over G. Square root of that. And that will be equal to square root of 2 times 1.2 over 9.8. And what you should get from that is 0.49487. I've kept as many significant figures as just to make sure I'm not going to have any mistakes. So I'm going to use this value now back over here. So I know how long it's in the air for. I know its horizontal velocity from above, which is 2.42 meters a second. So x is equal to 2.42 times 0.49487. And I get 1.1976 meters, or the 3 significant figures, 1.20 meters. There we go. So part C is calculate the velocity of the ball when it hits the floor. So again, we deal with the vertical motion. And we know that v squared equals u squared plus 2as. We can solve that by saying, therefore, the velocity at the bottom of the fall is going to be equal to 4.85 meters per second. So that's its velocity vertically once it reaches the floor. We already know previously that the velocity horizontally is 2.42 meters per second. So what we have is we have a ball that's sort of coming down and landing, and it has a horizontal component and it has a vertical component. So I need to find this vector, and it's telling me here above the horizontal, so it's also wanting me to find this angle here. So I can say that the magnitude of the force, or sorry, the magnitude of the velocity is going to be equal to the square root of 4.85 squared plus 2.42 squared, and what I get is 5.42 meters per second. So that's this answer here. And to get the angle, I know that I have VV and VH, I suppose, so I have the angle as being the inverse tan of 4.85 over 2.42. And what I get is 63.5 degrees. Cool. Okay, so for part D, I'm deriving an expression for the horizontal distance travelled in terms of the height of the ramp and the height of the table, and only those variables. So I remember that the distance travelled can be given by the velocity, the horizontal velocity of the ball after it reaches the bottom of the ramp, as well as the time that the ball has been in the air for from the top to bottom. So the first thing I'm going to do is remember that the horizontal velocity I solved in the first part of this question as being equal to 2gh. So the square root of 2gh. So I can get that there. And then the time that it's in the air for from above, I got over here, the time is equal to 2 big H divided by g, the square root of that. So 2 big H, this over g. Okay, so I have these two expressions here. That's not UV, that's time. So I have these two expressions here. Now I can sub those back into this equation here, and I get x is equal to the square root of 2gh multiplied by 2h on g. And what I notice is that these g's will cancel out. So I now have x is equal to the square root of 4 big H little h. Or I can also write that as 2 square root of big H little h. And there we go. Okay, so question 13, it's an absolute doozy. It's something that I'd imagine barely any students would have received 100% for, but apparently some did. It is something that you could easily attempt, but it'll be very, very hard to finish. So let's just go through it. What you've got is, it looks like a classic ladder question, leaning against the wall. The dimensions you've been given aren't relative to the size of the ladder, which makes things a little bit more complicated for the way I like to solve these ones. But the first part of the question is a fairly straightforward one. So it's asking you to draw and label the forces acting on the ladder. And you assume the reaction force at B acts at right angles to the ladder. So that's the one I'm going to draw first. I'm going to go over here and I'm going to push that out at right angles to the ladder. And I'm going to call that FB. The other force acting on this ladder would be here, where the person's standing. That's acting downwards. I'm going to call that FG, and then I've got the ladder itself, center of mass, acting down. I'm going to call that FL, and then I've got another force acting over here, and that is the tension in the cable. And then finally, there's another force here. Now, in a regular ladder question, you might be asked to work out what the angle is, but it specifically says here that it's an ice skating venue and it's a frictionless surface. So that would mean that the force from the ground is acting straight up, and I'll call that force at A. So where this gets hairy is looking at part B. So the question says, taking the moments around A, calculate the tension in the cable. So looking back at the diagram, if you take A as your pivot point, what you've got there, you've got 1, 2, 3, 4 forces acting on it, and you've got one that's acting counterclockwise, which is the reaction force from the wall at B, and then you've got clockwise forces acting mostly downwards, and the tension cable acting to the right. So to solve this, you need to start with your assumptions. So what I would do is I would say that the sum of all the clockwise torques is equal to the sum of all the anti-clockwise torques. So the clockwise torques, I've got the torque due to G plus the torque due to the ladder plus the torque due to the cable, in this case, or the tension. And that's going to be equal to the torque at point B. So that's my starting point. So let's go through and see how we determine these moments, or these torques, and put them into the equation, because this is where things get a little bit tricky, and it depends on your preferred method. In fact, I actually switch between methods when I solve it. So let's look at the torque from G. You can see that it's acting down, and we can see it's got a perpendicular distance of 3 meters. So that means the torque for due to part G, to the person standing on it, is going to be 3 times that force, which is a pretty easy one. Now for G, I use the perpendicular distance method, but to solve for the ladder, the perpendicular distance isn't known. But what I do know is I know the actual the radius. I know that that's 3 meters because it's halfway up the ladder. So what I'll do is I'll say that's 3 times the force due to that, and I know the angle here as being 45 degrees. So I say 3FL sine 45. And lastly, I have the tension in the cable, and I can use that using the same perpendicular distance method. So what I'll get is, in this case, it's just 1 meter away from the pivot point, and its force acting is tension. And that is going to be equal to the torque due to the reaction at B. Now, this is where I'm going to switch to the perpendicular force method again, because the force is given that's perpendicular. So all I need to know is the distance between A and B. Now, because I've been given this side here as 4, then I can say that the distance is actually going to be 4 over cos 45. So that's the R value multiplied by FB. So far, we're doing pretty well. We've got everything we need. Now what we need to do is resolve some of these. But the trickiest thing at this point is that I don't know what the value is for FB. I've been asked to find out what the tension of the cable is. So I have 2 unknowns. But there's another bit of information that I've been given that's going to help me. if I have a look over here, I've got a force acting in this direction, and that's FB. So what I'm doing is I'm just basically just going to draw this diagram again. And if I have a force there of FB, and I've also got a tension force. Now, see, the tension force is going to be counteracted only by FB. Notice that FB is the only force that actually acts to the left, which means that the horizontal component of FB is going to be equal to that tension. So by drawing this little vector diagram, I know that this angle here is 45 degrees. So from here, I can say that cos 45, so this is tension, cos 45 must be equal to the tension over FB. And if I bring that down to here, that would mean that FB is going to be equal to T over cos 45. So what I've been able to do is express the reaction force at B in terms of the tension. And so now if I go back down and I sub those in, and I'll start resolving some of those now. 99.8. And the next one, 15 times 9.8. So you can have just substitute an mg instead of the f, like I have. The answer key doesn't use FL or FG, they just use mg. Plus the tension, and that's going to be equal to 4 over cos 45 squared times t. Okay, so now I can keep working through that. I'll end up getting 2646 plus 312 plus t, and that's going to be equal to, so the cos of 45 squared I think is a half, so I end up with 8t. Great, and now what I want to do is I can say then that 7t, or 8 take 1t, so 7t is going to be equal to the summation of those, 2958. Therefore, t is equal to 423 newtons, or down here, 423 newtons. Okay, so on to question 14 now. You've got an energy level diagram, and the question's asking if you have a mercury atom, which this energy level diagram represents, and it encounters an electron of energy 23 electron volts. As that atom drops down states, what are the possible states that it could drop down to? So the first thing you want to do is, what is the highest that mercury atom could go if it absorbs 23 electron volts? So to show justification, you want to say, okay, what's 28.4, take 23.0 electron volts, and that's going to be negative 5.4 electron volts. So that's the highest sort of level it will be able to obtain. If you look at the diagram, you can see that means that n equals 3 is your max energy level. So once we've got that sorted, we can go up the top, and if we start from the 3, we can come down to the 2, or it could drop all the way down straight to 1, or it could drop down to the 2 and then drop down to the 1. So there's 3 energy transitions there. So moving on to part B, calculate the wavelength of the photon from part A that strikes the potassium metal plate. And that's where we need to go back and read the question. So it's talking about a filter that only collects electrons only collects photons that are produced from this transition from N2 to N1. So the first thing you want to do is work out what that wavelength, or what the energy level is, and then from there work out the wavelength. So we can do that just by first working out the change in energy. Using the diagram, we get 28.4, take 12.6, and we end up with 15.8 electron volts. We'll keep that there for now, and then we can then convert that using E equals HF, which is equal to HC on lambda. And so your lambda is going to be equal to HC on E. So 6.63 times 10 to the negative 34 times 3 times 10 to the 8. And that's going to be over your energy level. Now, importantly, we need to make sure that we convert this electron volts into joules, so times 1.6 times 10 to the negative 19. And if you do that, I got 7.868 times 10 to the negative 8 meters. So 3 significant figures, you'd write 7.87 times 10 to the negative 8 meters. All right, and there we go. And with part C, calculate the maximum velocity of any electrons liberated from the potassium metal plates. Now we're going into the photoelectric effect. So if you've got, what was the work function I think is given to you? So the work function here is given as 2 electron volts. So we would solve this by coming down here. So the kinetic energy of the electrons that are liberated, I suppose, is going to be equal to the energy of the photon minus the work function of the material. So that would be, if I remember correctly, it was 15.8, and subtract that 2 electron volts, and you end up with 13.8 electron volts. I'm going to convert this to joules now, and I've got 2.208 times 10 to the negative 18 joules. So now that I've got the kinetic energy, I know that that's equal to half mv squared. So the velocity is going to be equal to the square root of 2e on m, which I'm sure you've seen before. And we end up with 2 times 2.208 times 10 to the negative 18 over 9.11 times 10 to the negative 31. And what you should end up with, is I'll just write it here, is 2.20 times, not enough space, 2 times 10 to the 6 meters per second. And there we go. So part D is an interesting one. The first part's really, really easy, and how you go with the second part just depends on your conceptual knowledge. So the work function, which we've done, this has been done to death in our class anyway. So say the work function is the minimum amount of energy required to remove an electron from the surface of a metal. Okay, and notice straight away that I've already used half my space, which isn't very helpful for me because I need to answer the next part of the question, which is actually worth twice the number of marks. So part D is asking a very important question, and that is, why do the electrons ejected from the metal have varying degrees of kinetic energy? You know, we can work out the maximum kinetic energy, but why do they come out at different velocities? So the answer you want to say, or the answer that you want to give, needs to talk about how the electrons, as they're ejected, they're not necessarily gonna have a smooth trip out of the lattice structure of that metal. So something like not all electrons are released from the surface. Some encounter collisions and therefore have less energy than electrons released from the surface. Oh, just enough space. Okay, so question 15, you're looking at the classification of matter. In particular, we're looking at the kaon, and you've got a nice little table here which helps you identify what a kaon is. So the first question is, are they classified as baryons or mesons? And what you should have pulled out immediately is that all the different types of all the different types of kaons contain quarks and antiquarks. So you've got the neutral and the negative, and then you've got the antiparticle of those. So the question is, are kaons classified as baryons or mesons? So you would say they are mesons, and then justification of your answer needs to be put in. So I would say that all kaons contain a quark and antiquark, and then you would say mesons contain quark and antiquark. Therefore, kaons are mesons. Okay. Name the quarks that make up the K negative particle. So you've got the antiparticle of this one. So you'd have a strange, so what you've got is you've got a strange antiquark here and a down quark. So what you're going to have is the antiparticle of that. So what you would write down is you would have the strange quark and the down antiquark. Moving on, then you've got these K negative particles have a mean lifetime of 1.23. Awesome. And it's giving you a speed. So it's asking you what is the time if you were to measure it from an outside perspective. So if they have a mean lifetime, that'll be your true, or your proper time there. So I would say use your time dilation. So I'd have 1.238 times 10 to the negative 8. And 1 take 0.85 squared. And what I get is 2.35 times 10 to the negative 8. So it's longer, and that makes sense. So if I'm looking at this particle that's traveling really, really fast, then time elapsed on that time elapsed with that particle, according to me, will be slower. So 2.35 times 10 to the negative 8 seconds. Okay, so cans are produced, yep, no worries. So you can produce them and then it's being accelerated and then kept in a ring. So with the use of appropriate equations, explain how these protons were accelerated. Okay, so to accelerate them, you need to use electric field. And I'll pull this equation from my data sheet. So I can say F equals EQ. And then this force accelerates a particle, a charged particle. So I can say F equals ma. So where I really want to get at is the electric field creates an acceleration. There we go. And the next part is holding these protons in a circular path in the main ring. So charged particles again, we're talking about charged particles in a magnetic field this time. So charged particles experience perpendicular force, a force perpendicular to their motion, to the velocity in a magnetic field. So I can then relate these two equations together. So the magnetic force will be QVB, and the centripetal force, which is holding the circle, is going to be equal to mv squared on r. So I can say, therefore, QVB is equal to mv squared on r. Or I can go straight to r equals mv on bq. Alrighty, so looking at question 16, you've got a ball that's been swung in a vertical circle. So the first question's asking, what are the points in this diagram where the centripetal acceleration is the greatest? Okay, so your centripetal acceleration increases with velocity. So I would suggest in this case that the centripetal acceleration is its greatest at point A, because that's when it's traveling the fastest, and it's mv squared on r. The points where the tension of the string is the lowest, and that'll be point C. Now that's because at the top, the centripetal acceleration has been provided by gravity, which means the tension in the string doesn't need to be as high. Number 3 is, where is the net force not towards the center of the circle? Now, because this is vertical circular motion, at points B and D, there's also a component that's acting down, and that's what's actually accelerating it. It's making it go faster, not just go in a circle, which means at point B and D, the vector will not be pointing directly towards the center of the circle. And the points where the ball's weight force is perpendicular to the tension, well, looking again at this diagram, you can see that's exactly the case. So it would be at point B. So write an expression for the net force acting on the string at point C in terms of weight force and the tension in the string. So at point C, you've got two things that are providing that net force. You've got the tension in the string, and you've also got the weight force, or mg. So I would say that Fc is equal to the tensional force plus the weight force. And you could probably also write that as F net is equal to the tensional force. And in the marking key, they've actually expressed the weight force as mg as well. Part C is calculate how fast the 500 gram ball can be moving at point A for the 1.2 meter long string not to break. It's giving you a maximum tension there. So what you do is at A, you know, so at A, if we have a look, if I can scroll up, you can see at the bottom is where you'd have the maximum amount of reaction force. So that's where you would have the tension being the sum of mg plus the centripetal force, which is mv squared on r. So if you put that through, what you end up with is, you can rearrange it and get v squared is equal to t take mg, that's multiplied by r, and then divide that by m. And sum in the values, 172 take 4.9, that's going to be multiplied by 1.2, and divided by 0.5. And put that in a calculator, I've got 20.0 meters per second. And part D is calculate the maximum speed at which the ball can be moving at point C for the string not to break. My only disappointment with this particular question is that there's really not enough room for you to lay it out nicely. So what I would do is I would say, well, at the bottom you have a certain amount of kinetic energy, and that's going to have to be equal to whatever the kinetic energy was at the top, plus the potential energy at the top. And that way we can find the velocity based on this kinetic energy value here. So if I was to expand that out, I would have half mv squared plus, equals half mv squared plus mgh. So the masses don't matter. And I end up with a half v at the bottom squared is equal to half v at the top squared, which is the unknown, plus gh. I'm just going to move across here, it's a bit annoying, and you end up putting that in, you get half 20 squared is equal to a half v squared plus 9.8 times 2 times 1.2, because you've got to go 2 times the radius to the top. And what you would get is 200 is equal to 0.5 vt squared plus 23.52, and therefore your vt is going to be equal to the square root of 200 take 23.5, and that's going to be multiplied by that 2 value which we pull from the other side. And what I got was 18.8 meters per second. Again, there's really not enough space here, and if you look at the marking key, even they would have used a fair bit. So it's a bit disappointing, but other than that, it's a good question. Okay, question 17, the dreaded graph question. This one's on Young's double slit experiment, which is should be familiar territory, but perhaps not the graphing exercise itself. So what we've been given is 2 sets of data, and the first part is graphing x versus L. So I want L on the x-axis, and I want x on the y-axis, and it's saying to include a line of best fit and do not include the uncertainties. Okay, so here we go. So I've chosen a scale here that should give me a fair amount of dynamic range, so I should be able to get some good accurate plotting. Now it's just a matter of going through and making sure that I get each data point as accurate as possible. Now I immediately noticed that once I've plotted this third point that I'm not getting much of a straight line, so I can see that something might be either wrong with my accuracy, or it could be just an outlier in the graph. So it's something to keep in mind as I keep going through. Okay, so it's not the tidiest of all data, but it should be something that I can work with now. Now I just need to draw my line of best fit. It looks like this one here is going to end up being an outlier. Okay, so that one looks pretty good. That's the one I'm going to go with. I can see that it doesn't go perfectly through the y-intercept, but I never expected it to, so that's all fine. And I'm not including that outlier in my decision. And you can see that there's an area, there's a region just here where I've got a little bit of a gap, and here I've got a little bit of a gap, and they sort of they both go either way. So there's not much I could have done to sort of resolve that. So that's, as far as I'm concerned, that's a pretty good line of best fit. Okay, so for question 17, it's asking me to calculate the gradient of the line of best fit, showing the construction lines and using the correct significant figures. So I've already drawn in the construction lines and written my data points so I can save some time. I've picked 2 points here that are close to the range of values. I'll talk later about why that might be an important thing to do for this particular question. But you can see that I've got 2 sets of points, and I now just need to start calculating the gradient. So 1.54.5. 4.5, that's the first one, and that came after 0.44, 1.25. 1.25. So my gradient is going to be the rise over run. Now the rise is going to be the 4.5 take the 1.25, and remember this is in times 10 to the negative 2. If you have a look at that axis there, you can see that just there. So coming back along, and the run is going to be 1.54 take 0.44, which is going to be equal to, so 3.25 over 1.1 times 10 to the negative 2, and that's going to be equal to 2.9 I'm going to go to 3.0. So 3.0 times 10 to the negative 2. Since you've got meters divided by meters, the units are dimensionless. Okay, and the answer in the marking key, or what they wanted you to look at getting, was 3.2 times 10 to the negative 2. And that's pretty funny because if you put the data through Microsoft Excel and do a least squares regression on it, you get closer to my answer than you do to their answer. So maybe they made a mistake, but we'll talk about that one later. Okay, so for part C, if we have a look at our equation at the top here, we've got x on L is equal to lambda on D because n equals 1, so it's just going to be lambda on D. X on L is going to be equal to lambda on D. Now I plotted x on the y-axis, and then I had lambda on D like so, and then L was on the y-axis. So this one here was my y value on the graph, this one here was my x value on the graph, which means that this value here is my gradient. So coming on through, I get the gradient is equal to 3.0 times 10 to the negative 2, and that's equal to lambda on D. So lambda is going to be equal to 3.0 times 10 to the negative 2 multiplied by, and the value they give you is 2.19 times 10 to the negative 5. 2.19 times 10 to the negative 5, and what you should get, or what I get, is 6.57, so 6.6 times 10 to the negative 7, so the two significant figures. And their answer based on their gradient, which we've already determined isn't the right one, is 690 nanometers. All right. And this question here, okay, so for part D, it requires a little bit of usage of uncertainties. The method here, I believe, is a little bit flawed, and I'll talk about that one later on. So let's have a look. So it's saying basically to use your values and use their uncertainties to calculate an uncertainty in your gradient. So in our class, you're used to actually drawing the gradient to work out the uncertainty of the gradient. In this case, you're going to be applying the uncertainty of the values to the gradient, which I believe is an arbitrary way. And I think that if you pick a very wide gradient, you won't get the answer that they're looking for. So I'm hoping that they were a little bit nice to people on that. So if I just have a look at my range here, I've got it written here. So they're saying to use your values of part B. So what I'm going to pick at are these values here. So the range for the rise was 3.25 times 10 to the negative 2. And then once I did that, we get the range of the run, and that was 1.1 meters. Now the uncertainty in the rise, and this is where what they do in the answer key I don't particularly agree with. The uncertainty in the rise, they're saying, is related to the uncertainty in your y values here. So the uncertainty in that length, 0.002 meters for that one and 0.002 meters for that one. So if I come back down to here, you know, if you take 2 points, you got to have 2 times that value. So essentially it'll be plus or minus. In this particular case, it'll be 0.2 meters, and this one here will be plus or minus not 0.2 meters. It's a mistake. 0.4 because it's 2 times that uncertainty, and here it's 0.004. That's times 10 to the negative 2 as well. So it's the same number. I'm just representing it differently. Meters here and meters here. So look, this is an interesting way of looking at it, because what this says is the uncertainty in my rise is, no matter how I measured it, is going to be based on the values that created that gradient. And I'll explain to you in a second why I think that's a little bit of a shifty way of doing it. Let's work out the percentage uncertainty of the rise. That's going to be 0.4 over 3.25, and I get 12.3%. And let's have a look at the uncertainty in the run, percentage uncertainty in the run. That's going to be 0.004 over 1.1. You can see it's going to be a small number. And I get 0.36%. Right, so once you get these 2 points, then you add those percentage uncertainties together, because that's how you work out rise over run. So you would say the percentage uncertainty of the gradient, is equal to 12.3 plus 0.36. So we're quite happy to say that's say 12.7%, but I'm going to round up and say 13%. So, and since as well. Sort of. Now this is where I disagree with this idea, is that if I had have picked, if we go back to the gradient points, if I had have picked a larger range, so if I had have started my gradient from sort of down here in the corner, that would have increased the number, or increased the rise and the run. So these values here at the bottom would have been bigger, which meant the percentage uncertainty would have been smaller. And I could have picked them in such a way where the total percentage uncertainty of the gradient would have been less than 10%. Which is why I think that this method of using the uncertainties and then applying them to the gradient a little bit arbitrarily in this case, I don't particularly agree with. I think the best way to do it would be to incorporate your uncertainties as error bars and then work out your tolerances graphically. But this method does work so long as you pick a range which is sort of with the limit, giving you the limitation of the data spread as well. So notice that I've extrapolated backwards here, but I haven't picked a point in this area, and that has helped me get an answer that is consistent with what they've got. So I think this question is probably the funniest out of all of them as far as I'm concerned. But there you go. And the last question of section 2 is question 18. You've got a coil with a radius of 50 centimeters and a certain number of turns. It's moving through this magnetic field. And the first question is asking you to calculate the average EMF induced as the coil moves from B to C. So looking at the diagram, you've got no flux going through at this point, and then you've got a whole bunch of flux happening through here. So it's asking what is the average EMF produced during that change. So it's actually a fairly straightforward one. You have EMF is equal to your negative n change in flux over time. So I'll just work with that equation. So first work out the change in flux. It's going to be equal to the density multiplied by the area of the coil. So I would say it's 0.28 times pi r squared, 0.5 squared, and I got 0.2199 meters. Okay, and the time, we just say the time is going to be the distance traveled divided by the velocity. It's given the velocity as 0.8, and it's 2r on 0.8 because you want it's traveling 2 times the radius. So it's going to be 1 divided by 0.8. And the time is going to be equal to 1.25 seconds. So I've got this value and I've got this value. Now I can put that into my equation. So the EMF, the magnitude of the EMF is going to be 25 turns times 0.2199 over 1.25, and that's going to be equal to 4.398 to 3 significant figures, 4.40 volts. So down here, 4.40 volts. There we go. Part B is 8 marks for drawing a graph, which is a fairly hefty number of marks. And it's asking you to sketch the induced EMF versus time. Now, in terms of the peaks of the EMF or what those values are, it's not asking for that. So it's not asking how high it goes. It wants you to be specific on the x-axis, so for time. So what you need to know is essentially at what point in time does the coil reach each of these points. So it tells you that from A to F is 8 meters, which means that between here and here is 2 meters, and between here and here is 2 meters, which means that from here to here is 1.5 meters, and from here to here is 1.5 meters. Now that's important because what we want to find out is at what point does the coil reach just the tip of, or just the edge of that magnetic field, and when does it leave, and the same thing on the other side. So I'm going to use this page here to sort of draw that out. So I'm first going to say that at A, it's at A when time is equal to 0, and it's at B, and the distance being 1.5. So it's going to be there at 1.5 over 0.8. So T equals S on V, and that's 1.88 seconds. And C we mentioned before is going to be 2.5, so that's when it's on the other side. So that's when it's gone through two times the radius, which is 1 centimeter. There we go, and that's going to be 2.5 over 0.8. And I'm just going to finish that for all of these values. Okay, so from D is when it's on the other side. So what I actually did is I went backwards, right? So F is when it's going to be right at the end, and it's traveled 8 meters at a speed of 0.8. Oops. So it'll be 8 over 0.8. 10 seconds. So at 10 seconds, it shouldn't be inducing any EMF. In fact, if I go another 1.5, so remember it comes in 1.5 from the edge. So that means E is going to be, what's that, 6.5? And that's going to be happening at 8.12. On these, I round to the even number. If you round it up, you'd have 3.13 and 8.13. And D is going to be another one away from that, so 5.5. And that's going to be... So I'm just sorting out all of my numbers so I know what I'm doing. 6.88. So these are the times that correspond to the locations up here. But where you would have the peak is when you would have the maximum change in flux. So at that point there, so halfway between B and C and halfway between D and E. So I'm going to put that down here because they should represent when you have the maximum change in flux. So I would say the peaks would be at 2 over 0.8, which is 2.5. And the other one is between 5.5 and 6.5, so at 6 over 0.8. And I get 7.5. So what I need to the key things I need to get down are the peaks. So the 2.5 and the 7.5, I'm going to pop them in now. So at 2.5, which is here, and 7.5, which is here, is when I should expect the peaks. Now, it's going into the field and then leaving the field, which means that one is going to have to be, they're going to have to be opposite signs to each other. So I'm going to have the first one go up and the second one go down. Now, that's where my peak lies, so I'm just going to pop that peak there, and I'm going to pop this peak here, the same size, because it's moving at a constant velocity. Great. Now what I need to do is I need to pick up either side of the peak. So I've got 1.88 and 3.12. So 1.88 will be about there, and 3.12, or sorry, 3.12 is about there. Okay, and then the other pots are 6.88 and 8.12. So 6.88 and 8.12. Right. So now to draw my graph. It's going to be 0 outside of these times. So I want to draw a steady 0 line here, and then once I reach this value, I'm going to be peaking up and coming back down, and then I'm back to 0 again while I'm in the field. The field going through the flux going through the coil is going to be, the change in flux is going to be 0. And then here, because it's leaving the field, it's going to induce an EMF in the opposite direction, and then it's going to be 0 from this point forward. And there we go. So there's 8 marks in that, and yeah, it's a wide variety of how you could be awarded the marks, but I think the important thing would be to show the examiner that you were able to pick these points out, so that they know that you know what's going on. And that's it. That's the end of section 2. Okay, so looking at question 19, the first of the questions in the comprehension, we've got a standard article about mass spectrometry, and we've got a velocity selector and a little bit more about how that works. And then question part A is probably the easiest you'll ever come across. Writing an expression for the radius of the charged particle, straight out of your formula sheet, MV on QB. The next part is explain why it's important to make sure that all the ions that enter a detector have the same velocity. So since we're using the radius of the ion's path to find the mass of that ion, then we need to make sure that if we look at the equation at the top, that V, Q, and the magnetic field must be known, and they're kept constant for all the ions that pass through them. That way the path differences that you see are only due to the differences in the mass of the ions rather than differences in, say, for example, the velocity. So question 19. You've got a table here, that's great. An unknown ion enters the detector at 9.24 times 10 to the 4 meters a second, and now you need to find out what that mystery ion is. So it's just giving you enough information and no bonus points for figuring out that you're going to need to use this equation. So rearranging the equation, you can get the mass by itself, QB on V. I'm going to quickly convert the radius from, or calculate the radius based on the diameter. So remember, it's traveling in a semicircle, so the distance is away from the detector. If you look at that diagram on the other page, shows it's a semicircle, so the radius of path is half of what that distance is. There we go. Okay, so now subbing in those values. So R is 0.0619. So I'm going to put Q as just the one positive charge. And if I don't get a value that is consistent with anything in the table, then I'll just double that number and then even triple that number just to see if I get any hits. So at the moment, I'm making the assumption that the ion is a single positive charged ion. Like that. And if I put that in my calculator, I've got 3.75 times 10 to the negative 25. So I actually have got a hit here of 3.75 there using that charge value there. Okay, so that's 3.75 times 10 to the negative 25, and therefore the particle is going to be radium positive. Okay. Part D is calculate the accelerating voltage needed for the ion to attain a certain velocity. So you got your particle accelerator formulas. So work is Q times the potential, which is what we need, and that work is going to be done to give the particle some kinetic energy. So to solve for the voltage, it ends up being mv squared on 2q, which is going to be equal to the mass 3.75 times 10 to the negative 25 times the velocity squared. Now when I first did this, I forgot to square it, but it was very obvious. I got a number that didn't make sense. Divide that by 2 times 1.6 times 10 to the negative 19. And if you do this, you'll get a number of 10,005 volts. So down here, I would write it as 1.00 times 10 to the 4 volts. And there we go. Question E, the velocity selector, shown on page 29, uses a combination of electric and magnetic fields. The ions travel directly across the selector panel. So the important thing is it says that it travels directly across the selector parallel to the charge plates. And what that means is the path does not change. So what you want to say is for path not to change, no net force. Therefore, you'd expect that the force due to the electric field has to be equal to the force due to the magnetic field. So the electric field is F on Q. That's what you get on your formula sheet. So I'd rearrange that to say, well, the force electric field is going to be equal to EQ. That has to equal the magnetic field, which is QVB. The Q's cancel out, so I have E equals VB. So the velocity is going to be E divided by B. There we go. Okay, question F. Explain in detail, that's interesting, why an ion traveling at a velocity greater than the selected velocity would not enter the detector. So there's a detector there, so why does it come through but not make it through there? So we know that obviously the force is unbalanced and it's deviated somewhere. So I'm saying that if the ion is traveling too fast, then it'll experience a greater magnetic force because you've got F equals QVB, and that means it'll have a net upward force, and the particle will then deviate upwards and obviously probably collide with the wall or the barrier instead of passing into this entry over here. So if I was to draw that diagrammatically, I'd draw the path of the particle, and then I would, I wouldn't expect you to do this, but I'm just sort of demonstrating here. It's got a downward force, which is due to the electric field, and it's also got an upward force due to the magnetic field. Now, if both of those are equal, then yes, its path will go into the, its path will follow through and it will go into the detector. But if FB is greater, then you'd expect a curved sort of pathway. Now it'll curve all the way except once it leaves the field it won't curve anymore. So you want to show that it's going to collide with that wall and that it's got a curved path up until that point. And that's it. Okay, lucky last, question 20. So we've got an article here that was taken from the ABC, and abbreviated obviously, and then some questions at the end. So I'm going to assume you've read the article. The first part of the question is to estimate how much time it takes for the plasma from a typical coronal mass injection to reach the Earth's magnetic field. So you've got some information here. I think in the article it says that it travels around, I was trying to highlight it here. So it travels around 500 million kilometers before slamming into the Earth's magnetic field, and it tells you how fast it's going as well. Okay, so let's put that information in to make our estimates. So, it travels 150 million times 10 to the 6 kilometers, so 10 to the 3 meters, and the speed that's traveling at is 6 million again. Kilometers per hour, so I'm going to divide it by 3.6 to get it in meters per second. So my time that's going to take is going to be the distance divided by the velocity. So those will cancel out there. So I've got 150 times 10 to the 3 over 6 over 3.6. And what I get is 90,000 seconds. Now it's asking for hours, so I'm going to convert that to minutes by dividing by 60, and I get 1,500 minutes. And then when I divide by 60 again to get in hours, I get 25. So 25 hours is my answer. For part 2, it's asking for 2 reasons why my answer is only an estimate. And there's 2 things that sort of give it away. So in terms of the estimate part, this word here travels around 150 million kilometers. And here it says varying speeds. So what I'm going to do is I'm going to bring that up here, essentially just quoting the article. So I'm going to say comes in at varying speeds. Oops. And part 2 is it travels, the keyword being around 150 million kilometers. So I want to really highlight those points to the examiner about why I'm using an estimate here. And part B is draw the possible path of a charged particle traveling along the magnetic field line after approaching at an angle other than 90 degrees. Okay, so I've got this particle here that's coming down. Now, if this particle is going perpendicular to the magnetic field, then we know that it's not going to interact with that field at all. The only thing that makes it turn is the part of it that's traveling perpendicular to it. So what actually happens, and you've probably seen this in demos, is as the particle sort of moves at an angle, only its perpendicular component of the velocity actually goes in a circle. So what happens is it goes into a spiral. So what you would draw is a spiral, and the velocity will remain constant, but importantly it says here that the field strength increases as the particle moves towards the pole, which is what you'd expect because all the field lines come together. So if the field strength is increasing, then you know that the radius of that turn will decrease. So as you come closer to the poles, what you would need to show is that the radius of that turn gets smaller. So something like that is what you would draw. In question 20, it's asked to draw the magnetic field around the Earth, and it is horribly difficult to do this sort of thing, so I understand that you might have had some trouble. So I'm just going to draw. Now remember, you sort of picture it like you've got a magnet in here with the North Pole at the bottom and a South Pole at the top. So if I was to draw that, you know, you can turn around and then you got yourself your field line like that. And it comes out. Now, as you get further away, you want to show that the density of those field lines starts to decrease as you're further away from the Earth. Yeah, I'm pretty happy with that. I mean, it's not the best, but I don't have any quick way of doing it, so that'll be the way I'll do it. So something like this is fine as long as you're showing things like if it's going from the South Pole to the North Pole is those field lines, and you also want to show that the distances between adjacent field lines get smaller as you get closer in, to demonstrate that the strength of the magnetic field decreases as you get further away from the Earth, and also that you have this sort of condensing of the field at the poles. Okay, and part 2 of this question is, using the information from the text, suggest a reason why auroras are usually seen at the north and south poles but not at the equator. So the text has some clues about this, but it's not as clear as what I would like it to be. I think that some prior knowledge in this might be helpful. So it's telling us that they travel along our planet's magnetic field lines towards the north and the south poles. So similar to that diagram that we drew here, they travel along the magnetic field until they reach the poles. Now, if they're sort of following those lines, you'd expect that they'll condense up. So this is how I'd write it. So the plasma travels along the magnetic field lines towards the poles at high altitudes, and then as they reach those poles, they can follow the field in or downwards towards the lower altitudes, and they can interact with the atmospheric particles. And that's also I think it's particularly a stronger point when you have the magnetic field lines are closer together as well. So you're going to have a lot more interactions happening where they all sort of converge, and that creates the excitation of those atmospheric particles. And then as those atmospheric particles sort of drop down to the ground level, that's when they release those really colourful colours. And lucky last, we have question D, which the examiners say was pretty poorly done by everybody. So I'll try to go through it with as much detail as possible. So the question's asking using specific information from the passage, and I think this is probably where some people might have tripped up. Explain why the same photon-producing electron transition process produces red light in neutral molecular nitrogen and blue light in ionized molecular nitrogen. So it's basically going to be comparing what happens with neutral and ionized molecular nitrogen. So the first thing we're talking about here is it has red light and blue light. So I'm just going to point out, just in case the examiner doesn't know that I know this, but red light has a relatively low energy, and blue light has relatively high energy. So now I'm going to start digging into the article and see what I can find. It's all at the bottom here. Molecular nitrogen glows blue after being ionized. The electrons now tightly bound. Now this is the key, the tightly bound due to ionization. So when the molecular nitrogen has been ionized, the electrons are tightly bound. So what that would mean, so I'll come up to here, and what I want to say is basically repeating what the article says. Okay, so I've said when ionized, electrons are more tightly bound, so that's from the article, and then going further into that, I'm saying that this means that it requires more energy to excite those electrons from the plasma, and if they do get excited, they need to come back down, and as they come back down, then they're going to undergo a larger energy transition. So as they come down through a larger energy transition, they're going to be releasing photons with more energy, more frequency, and therefore you have a reduced wavelength, so more bluish or more blues are going to be released when compared to, say, neutral molecular nitrogen, where, as they say, the electrons are not as tightly bound. And that's it. That's the exam done. Well done.